This video talks about the nature of science and a lot of different topics involved with that, such as the difference between science and pseudoscience, theories and laws, um, what empirical evidence is, the difference between observations and inferences, accuracy and precision, and how we represent our data through different types of graphs in science. To start off with, we'll just talk about science and pseudoscience. So science is it's based on real data. It tries to explain our natural world or describe a natural world and understand why it works. For example, astronomy. We study the stars and the planets and how celestial bodies interact with each other. Chemistry is really good at describing what things are made of. Biology is the study of life, and physics is the study of just about everything else, motion and electricity and forces, things like that. Pseudoscience is not based on data. For example, astrology is a really good one, or horoscopes. Basically, people try to say that your day is going to go a certain way based on how the stars are aligned or how the planets are aligned. And there's no scientific data to back that up. Homeopathic medicine, which sometimes can help because it makes you think that it's going to work, so your brain tricks you into feeling better. But most of the time, it's just a trick. We call that the placebo effect. And biorhythms are really fun. If you Google those, it'll ask you to put in your birthday and birth year, and based on how the planets were aligned when you were born and how long you've been alive, it tries to tell you the different months of the year whether you're going to have good emotions or bad emotions, or you're going to make a lot of money or not a lot of money. It's definitely unscientific. This is a pretty good cartoon that explains pseudoscience and how most scientists or doctors feel about it. But this person goes into the doctor with some pain, and the doctor says, "Well, you know that your pain might be due to your yin and yang being out of celestial alignment. But let's just humor me and see if your broken arm has anything to do with the problem." Scientific theories versus scientific laws. Scientific theories explain why things happen. They are based on data, and they can change if we get new evidence. Scientific laws, though, they just describe things that happen. Natural phenomena. It just tells you what happens. It is also based on data, but it doesn't change because generally in our world, the things that have always happened will always happen. One good example is the law of gravity. It's a law because the law of gravity says if I drop a ball from 4 meters high, it's going to fall. That's it. That's all the law of gravity says. It says that the earth or that things get pulled towards the earth. The theory of gravity tries to explain why that happens. There have been a lot of theories to go with why that happens. Our current one is that compared to the ball, the earth is so massive that actually the way gravity works is two objects will have the same force of attraction on each other, but since the ball is so much smaller, it's the one that moves. It gets pulled in towards the earth. So hopefully that illustrates the difference between a theory and a law. And then we have empirical evidence. The word empirical comes from the Greek word for experience. What empirical evidence means, it's scientific data that we get through experiencing things. So we could experience we could experience something and make observations, and that would give us some data. Or we could experience through an experiment and do like a professional scientific experiment and collect data that way. But empirical evidence is just a fancy word for scientific data. Now, I just mentioned observations a little bit, but in case you didn't know, an observation is one type of data collection. We usually use our five senses for it. So maybe you could see something or taste or smell or hear or feel something and make an observation about it to help describe. When we make an observation, that helps to collect or helps to add to our collection of data. And it is one way to get empirical evidence. An inference is an educated guess based on your observation, or I like to say is an interpretation of an observation. One example I like to use is if you notice in our classroom, there's one wall that's green. That is an observation. You could walk in and say, yep, that wall's green. I just observed that. But you could infer that maybe that wall is green because your teacher likes the color green and he had it painted that way. You have no actual evidence to back up your inference, but you do know for sure that that wall is green. So it might be true. You're not sure. It's a good guess, and you can probably test it out or do some research to figure out whether that inference is correct or not. We also have accuracy versus precision. This is very easy. A lot of people get this confused. Accuracy is just how close you are to the right answer. Precision is how often you can get the same answer. So if I am accurate and precise, I'm going to hit the bullseye each and every time. If I am precise but not accurate, I'm hitting the same answer, but it's probably not the right answer. And we say there's a systematic error, or there's something wrong with your experiment, and maybe your something's not calibrated right. So you keep getting the same answer, but it's just not the right one. You could have something that's accurate but not precise. That means you get close to the right answer each time, but it also kind of strays away from that. You don't have them all in the same exact spot. So maybe your numbers are a little bit far away from each other, but they all kind of center around that correct answer. And then if you're inaccurate and imprecise, you're not really that close to the bullseye, and you're not close to other answers. Finally, we'll talk about graphs a little bit. Graphs are really important for scientists because it helps us to represent all of those numbers, all that data we collect from our experiments. It's nice to write down numbers on a table, but it's a lot easier to visualize what's happening in our experiment if we put it on a graph. We can analyze that data and try to understand the patterns better when we graph it. And then if we see a pattern in that data that's different than we expect, we might have to go on to the next scientific step, which would be to test it again, or to maybe try to rework our hypothesis or our current theory and try to better understand what we're dealing with. So there's a few types of graphs. The four main types of graph are bar graphs, line graphs, pie graphs, and pictographs. All of those are really fun to look at, I think. But in science, most of the time we use the line graph. There are a lot of times when bar graphs are really important for science too. Pie graphs are really great for illustrations for like a report that you're doing. Maybe if you collect a poll from a lot of different people and you're trying to get opinions, you might put it into a pie graph to help visualize what percent of people feel a certain way. And pictographs are like sideways bar graphs, but they're more fun because you put pictures on them. Anytime you make a line graph, which are the graphs that we'll be dealing with the most in science class, there's a couple important parts that you really need. For sure, you need the graph title, which tells you what you're graphing. And the graph title usually, always has y versus x, or whatever the y-axis is dealing with, versus whatever the x-axis is dealing with. So in this case, this graph is talking about how much motivation students have compared to how many days at school they've been. So motivations on the y-axis. So you put motivation versus days at school, and that's your graph title. It's very easy. We also need axis titles, which tell us um, what each axis is talking about, and we always want to include units on that. So in this case, the y-axis is motivation, and we're measuring that by how many tasks a student is willing to do. And the x-axis is days at school, measured in, you guessed it, days. Those words are nice, but we also need numbers. So we put numbers on the x and y axes to tell us exactly how many of those units we're dealing with. And then you graph your data. And for a line graph, you draw a line through it. And if you were like to analyze graphs, just take a look at this one. You notice that the longer you're at school, the less likely you're probably going to do or have a lot of motivation to complete a task. I think you'd all probably agree with that.